Okay, so during the previous session, we have finished with the notion of arbitrage free price. Okay, so put the mask, please, everybody. So it's a theorem that I have stated, okay? So the set of arbitrage free prices, okay, for the contingent claim U was the following. It was simply the expectation, okay, of the actualized payoff, that is U, with respect to an equivalent martingale measure. Okay? So we have finished with this during the previous session. And the idea, to begin with today, we are going to describe this set exactly. And in particular, we are going to prove that under the no arbitrage hypothesis, this set is an open interval. Okay? We are going to show this. And we are going to see the consequence of this one. Do you have some question before I start? So do you remind what we have done? Yeah?
Quelle est la différence entre l'espérance normale et l'espérance...
C'est la même chose, hein?
D'accord.
This is just, it's a notation for it's just, I precise when I do this the fact that I consider okay, the expectation with respect to Q. Because initially I have a probability that was P, okay? So what I have denoted by E was the expectation under P, and just to remind that here I take the expectation under Q, I just use this notation, so it's an expectation in the classical way, but with respect just to the probability Q. Okay? So nothing new. Okay, so let's continue. This one, so was a remark I have finished with, but what happened if U belongs to calligraphic K in this situation here? What is this set? Zero. Why? Because I am in K. Okay, it means that I am the final value of a self-finance strategy starting from 0. Under Q, the value of this strategy is 0. So in expectation, okay, it is constant and equal to its initial value, that is 0. So in this situation, this set is reduced to a singleton. Okay, so definition in order to introduce quantity that we are going to use hereafter. I define by M overline U by the supremum of these quantities here. Okay? So the supremum of these numbers. Okay? And by M underline U, the infimum of this quantity. You are going to see, so first that I will use this one in order to describe what is exactly this set. In fact, we are going to prove that it is the open interval, okay, corresponding to these bounds. And what is more, a little bit later, we are going to see that if I am not able to replicate a claim, this one will be the minimal over replication price. Okay, so it's what we are going to see today. Lemma 11. Okay, so if I suppose that NA is fulfilled, meaning that there exists at least one equivalent martingale measure, and meaning that this set is not empty, okay? I said that I have only two possibilities. But the case where these two numbers are equal, or the case where they are different, okay? So then, M overline U is equal to M underline U, okay? The first possible situation. And in this case, in fact, U is replicable at price M overline U, okay, and the set of arbitrage through prices in this situation is just reduced to this situation. It's an extension of what I have done here. If I am in K, it means that I am replicable at price 0. Here, if I am replicable, it will be at this price, okay, and the set of arbitrage-free prices will be reduced to a singleton. Or, second possibility, that M overline U is strictly greater than M underline U. And in this case, U is not replicable. It means that you will have a criteria to see if I am replicable or not. If I have the equality between these two quantities, I am replicable. If I have a strict inequality, I am not. And in this situation, and the set of arbitrage prices in this situation is the open interval M overline U and M underline U M overline U. Okay, so you have a perfect description of what happened if NA is fulfilled. If I have equality between these bonds, I am replicable at this price, and the set of arbitrage-free prices is reduced to this singleton. If I have a strict inequality, I am not replicable, and my set of arbitrage-free prices, okay, is in fact a continuum. I have an infinity of arbitrage-free prices given by this open interval. Okay? So we are going to prove this one. Okay. If I have the equality, I have to prove that U is replicable at this price. Okay? If I define by F, U minus what? Minus M overline U. What can I say about this quantity? I can say about this quantity that for all Q belonging to the set of the equivalent martingale measure, what can you say about this quantity? So why it's 0?
Because M of U under Q is the expected value of U.
Yeah.
And this is the unique variable.
Okay. So it's this one, okay? I know that I have a single point in my set of arbitrage-free prices, okay? So necessarily, it implies that all these values are equal to M overline U, independently of the choice of the equivalent martingale measure, because I have a single point inside, okay? So it means that for any Q, but I know that this expectation is 0, okay? And what I can deduce from this is something we have already seen together. What can you say of a random variable F that fulfills this one? What can I say about such a random variable? It's an argument I have already used. Okay. So it was a result which name lemma 10, okay. F belongs to calligraphic K, and in fact it's finished, because what is the meaning of being in calligraphic K? It means that I am, in fact, this kind of quantity for H belonging to HD, and so F is equal to what? Or U is equal to what? U is equal to M overline U plus H S capital T, meaning that my contingent claim is replicable at this price. Okay? So it's not that complicated. The only thing to have in mind here is that since I have a single element in this set, all the expectation under Q are equal to the same number. Okay, that is in fact this one, and so the expectation under Q of F for any Q is equal to 0. I can deduce that F is in calligraphic K, and so that I can make U replicable this way. Okay. So I have this one. So I have done the job in this situation, where when these two quantities are equal, I am replicable. Okay. Do you agree with what I have written? Okay? So, what happened in the other situation? So first we are going to prove that in this situation it's not possible for me to be replicable. Okay? And then we are going to prove that the set of the arbitrage price in this situation is equal to what? To this open interval. Okay? So, the proof of the second part. Let's suppose that U is replicable. So if U is replicable, I can write U as small a plus HS capital T. Okay? I can write it this way. And what can I say about this quantity here? What can I say about this quantity? Okay. So I have a problem, because if I suppose that M overline U is strictly greater than M underline U, it's not compatible with the fact that my expectation is constant in Q here. Okay, so it's not possible for me to be replicable. So contradiction. Okay, so it's not possible for me replicable. So the condition to be equal or to be strictly greater for these two numbers is a perfect characterization of the fact that I am replicable or not. So the last thing to prove is this one. To prove that the set of arbitrage reprices is given by this open interval. So let's see what happens. So first, I can say the following. By definition of the fact that M overline and M underline are respectively the lower and the upper bound of this set, I am sure that I have, okay, I am sure that I have this inclusion here. No, I have to be careful. So it's true what I write, okay, but I have to be careful about this. So I want to prove that I am equal to the open interval, having in mind that these are the lower and the upper bound of these values. I said first that this term is an interval of R. Why I have this? Do you have in mind the characterization of what are the interval in R? In R, okay, what is nice concerning intervals? Yes. In R, to prove that I am an interval, I have to prove that I am convex. Okay? So, convex in this situation, of course, it's because I am in R here. Huh? If I am convex, it's equivalent to be an interval in R. So why I am convex? So it is possible to take a convex combination and to prove that I am still inside, okay, but I have a more elegant way in order to do this. If I define phi this way, so I remark that the set of the arbitrage free prices is just the image of the set of the equivalent martingale measure by phi. Okay? What can I say about phi? Yeah. And we. So phi is linear. Okay. And what is interesting with linear mapping is the fact that they transform a convex set into a convex set. Okay? So if I prove that the set of the equivalent martingale measure is convex, I will have the convexity of what I want, and so the fact that I am an interval. Okay? So why this one is convex? So we have already seen together that I have a characterization of the set of the equivalent martingale measure, that is Q belongs to the set of the equivalent martingale measure if and only if for all k belonging to calligraphic k, the expectation under Q of k is equal to 0. So you see that if I use this characterization, okay, if I modify Q in a convex way, I preserve this equality here, and so the set of the equivalent martingale measure is a convex set. So it is convex because of this characterization, and so phi of ME of S, that is the set of arbitrage prices, is convex. And since it is convex, it is an interval of R, okay, from a well-known result. So now, I know that I am an interval, okay? So I have to prove that I am the open interval. And here I don't have the choice, okay? So if this one is an interval, from the previous definitions, I know that this interval is included in this open one, is contained in this open one, excuse me, and is included in the related closed interval. Okay? I just say that if I am an interval, okay, if I consider my upper and lower bound, I am included in the closed interval containing the lower and the upper bound, and I contain the open one. Okay? So to conclude, we have to prove what? We have to prove that the bounds are not inside. Okay? So we have to prove, so to conclude, we have to prove that M overline U and M underline U are not in this one. Okay? Knowing that that I am an interval, if I prove that my upper and lower bound are not inside, okay, I will have the job. So I will do half of the job. So I will do for the first. It's a good exercise to do the same at home for the other one. So let's prove that this one is not inside. We are going to suppose the contrary and see what happens. We are going to obtain a contradiction. So, suppose that there exists Q belonging to the set of the equivalent martingale measure such that M over IU is equal to the expectation under Q of U. And that is, I want to prove that this one is not inside. Let's suppose the contrary and see what happens. And we are going to see that we are going to have a contradiction. So, it means that my upper bound is reached. Okay? I can attain my upper bound. Since I know that this set is an interval, it means that there exists Q tilde belonging to the set of the equivalent martingale measure such that if my upper bound is reached, it means that there exists a point below. That is such that the expectation under Q tilde of U is strictly less than the expectation under Q of U. Why it's the case? Because if I suppose that my upper bound is inside, it means that there is a point below in my interval. My interval that is defined this way. So typically, I can write the following. So I have this strict inequality here. Okay? And the idea will be to play with this strict inequality here to obtain a contradiction. And what will be my contradiction? Don't forget that M over line U is the upper bound. Using this one, we are going to prove that it is possible to find an equivalent martingale measure, okay, such that the expectation of U under this equivalent martingale measure is strictly greater than this one. And in this way, we are going to obtain a contradiction because this one is the upper bound. So it's not possible to be strictly greater than it. Okay, so the idea, intuitively, this one means that if I allow to consider the expectation with respect to negative measure, I have this one here, this expectation that is strictly positive, okay, and this strictly positive quantity will be the one that will help us to do the job. So we are going to consider, okay, this one. Q epsilon, that is what? I start from Q, okay, the one that reached the maximum. And we are going to modify it a little to take advantage of the fact that this quantity is strictly positive. So we are going to transform it a little this way. So I have here, with my notation, Q minus Qt. So be careful, if I do the job this way, I don't know what is the sign of this one. Okay? But if epsilon is small enough, fixed but small enough, okay, I am sure that Q epsilon, okay, is a positive measure, for sure. Keep in mind that here I have vectors with finite number of coordinates. So if I take epsilon small, okay, I am sure that I have a vector here with, okay, components that are in fact strictly positive. Is a positive measure and in fact a strictly positive. What can you say about the sum of all the coordinates of this vector here? So Q is a probability, okay? So if I do the sum of all the Q epsilon W for W belonging to omega, I obtain what? 1, because I have 1 for this one and here 0, okay? Is the difference. So I obtain 1. So you have here Q epsilon. That is a probability, in fact, equivalent to the historical probability. And I say that, in fact, this one is an equivalent martingale measure. So why it's an equivalent martingale measure? Q epsilon is or belongs to the set of the equivalent martingale measure because it's something that is equivalent to P. And because for all k belonging to Kaiser k, what can I say about the expectation under Q epsilon of k? So Q is an equivalent martingale measure. So the expectation under Q of k is 0. The expectation under Q of k is 0. The expectation under Q tilde is also 0. So I obtain 0. And that's why I have an equivalent martingale measure. It's the characterization I have used previously. Yes?
Epsilon is strictly positive?
Yeah. Small but strictly positive because I want something that is so small, okay, enough, and strictly positive. Yeah? No, I want to prove that it is equal to the open one. It is included, huh? I don't have an equality here. I just say that if I speak about an interval AB without doing any hypothesis on the bounds, they may be inside or not, I will always be in this situation. Independently of the fact that the bonds are in or not. Okay? An interval with finite bounds that are inside or not, whatever, contains always the associated open interval and is always contained in the closed one every time. Okay, so if you take numbers, okay, I don't know if you have something like this, for example, okay, 1, 2 will be included in 1, 2, and will contain 1, 2. It's just what I said here. Okay? I know that I have an interval here. Okay? M overline U is the upper bound of all these values. M underline U is the lower bound of all the values. So I have necessarily this one. Now, my objective in the proof here is to prove that, in fact, this one is this one. I have already proved that I am an interval, and now I prove that the bonds are not inside. If I prove that the bonds are not inside, I will be in this situation here. Okay? So I have a probability equivalent to P that is an equivalent martingale measure. And now to conclude, I have done the job exactly to obtain this. Okay? So if I consider the expectation under Q epsilon of U, what I obtain, I have this formula here. So I have the expectation under Q of U plus epsilon, the expectation under Q of U minus the expectation under Q tilde of U. And what can I say about this quantity? I know that this one is equal to M over line U. That is my upper bound. And this one is what? It is strictly positive. So I have this one that is strictly positive. So at the end, this one is strictly greater than M over line U. It's not possible because M over line U is the supremum of all these kind of quantities. So it's not possible to find one that is strictly greater than M over line U, implying that it's not possible to have this, and so I prove that this bond is not inside the interval. I can do exactly the same job for M underline U, that is the lower bound, okay, you do exactly the same, and you prove exactly in the same way that the lower bound is also not inside, so my interval will be the open interval M underline, M over line. Okay? So in the case of what we have done, that is, keep in mind that we are in the part where I do, okay, I am in a static part in the sense that I have my initial market, I have added one claim that I am able to buy or sell, okay, at time t equal to 0, and I do nothing until the end. And I have proved that if I want to impose a constraint on the initial price in such a way that the new market becomes or stays arbitrage free, I obtain the set of the arbitrage free prices, and I have a perfect characterization of this set. Okay. If my contingent claim is replicable, then this set is a point, and if it is not the case, the set of the arbitrage free prices, okay, is an open interval, okay, described perfectly by these bounds. Okay, so it's what we have done. So now we are going to do exactly the same, but considering that the contingent claim may be buy and sell at any time, not at time t equal to 0. So we are going to consider the dynamic notion of the price, not considering only that I can buy or sell at time t equal to 0. Okay, and we are going to see that we are going to have big links with what I have done here. In fact, the static case is in fact all what I need to be able to do, okay, to pass from the static to the continuous one or the dynamic one, okay. The things are exactly the same. So do you have some question concerning what we have done? So I have done the proof. Doing this, I have proved that the set of the arbitrage free prices, in the case where U is not replicable, that is in the case where M over line U is strictly greater than M underline U, is necessarily the open interval. Okay. M underline U, M over line U. Okay. Yeah.
Maybe a stupid question.
No.
How do you know there exists a feature in M such that there is inequality on the right?
Yeah. It's not a stupid question. It's because I know that I am an interval. Okay. So if you have an interval, if you suppose that the upper bound is inside, you have necessarily a point below. Okay. It's because I am an interval. I have a continuum of value before, and I can find one that is strictly less. In the same way, if I suppose for the second case that the lower bound is inside, it will be possible for me to find someone that is strictly greater inside, and I will do exactly the job, just inverting the things. Okay. So I erase if you don't have questions. Okay. Now, let's do it in a dynamic way. Okay, so it's the part B of this subsection, dynamic approach. Okay, so first the definition. So previously I have defined an arbitrage-free price, and now we are going to define what is an arbitrage-free price process, something that depends on the time. Okay, so you can define it this way. So AT, t belongs to 0, capital T, is an arbitrage-free price process for the contingent claim U if two conditions. First, A capital T has to be equal to U. Okay, because if I want AT to be the price, okay, of course the final price has to be equal to the contingent claim, as in the case of a European option, you know that the final price is equal to the payoff. It's exactly what I impose. Okay? So if A capital T is equal to U, and if the market with D plus 1 risky assets. So keep in mind that initially I have in my market S1, if I write them in the actualized way, SD, the D risky assets. We are going to add A and consider it as a new risky asset. And what I want, if the market with this plus 1 risky asset fulfills and A. So this is the definition of an arbitrage-free price process. That is a stochastic, discrete process with a final value equal to my contingent claim, and such that if I add this process as a new risky asset in my market, then okay, I preserve the fact that the market is without arbitrage opportunities. So it is more or less the same idea as the one I have used in the static way. In the static way, it was just, okay, I can buy or sell at time t equal to 0. I do nothing until the end, and I try to see what happened for the initial price if I want to preserve the absence of arbitrage opportunity. And here I do exactly the same, but in a dynamic way, okay? Defining the price at any time. So let's see the following lemma, that is, we have already done all the job in order to characterize, okay, what is more precisely such an arbitrage-free price process. Because in few words, here, okay, we have proved in theorem 1 that if I consider a market as defined in the beginning of the course, the no arbitrage opportunity is equivalent to the existence of an equivalent martingale measure. But in fact, I have done the job for D asset with the fixed D. It means that if I add one more asset, I have exactly the same kind of theorem. It's just that I applied the theorem for D plus 1 assets instead of D. I have yet never used, okay, in the proof, the fact that I have a particular D. It was for an arbitrary D. Okay? So if I impose the market with D plus 1 assets to be arbitrage free, it means that there exists an equivalent martingale measure for this asset. And what will be an equivalent martingale measure? a probability equivalent to P that make all these values martingales under Q. But if all these values are martingales under Q, in particular, this one are martingales under Q, meaning that the equivalent martingale measure in the new market is also an equivalent martingale measure for the previous one, the original one with the D risky assets. Okay? So what we are going to say now is that if I am an arbitrage free price process, in fact, there exists a probability equivalent to P making this one martingale, that is someone belonging to MES, the set of the equivalent martingale measure in the initial market, that make this one a martingale. So it's exactly what we are going to write. So if, let's take the initial market, so the one we have previously studied, if the initial market, so the one with the D risky assets, fulfills NA, then, so it means that there exists an equivalent martingale measure, okay, for the market with these D assets, then AT is an arbitrage free price process if there exists Q belonging to the set of the equivalent martingale measure of this market, such that what? But that also make A martingale under Q. That is such that AT is equal to the conditional expectation under Q of U given F. And in fact, here, you see the relation between this notion of arbitrage free price process and the fact that you usually know that a price, when you do mathematical finance, is given by a conditional expectation with respect to an equivalent martingale measure. It's just come from the definition I give for the arbitrage free price process. And this one is in fact the real ID of Black and Scholes. Okay. The idea was not to take the exponential of a buoyant motion because it's just to make the price of the risky asset positive, okay, using the buoyant motion inside. The idea was to propose the notion of price, taking into account, okay, the notion of arbitrage opportunities and the fact that the assets are replicable or not. So here, what I will consider as a fair price will just be a price associated to a contingent claim that preserves the fact that my market is without arbitrage opportunity. So this notion of price is intrinsically linked to the fact that I don't want arbitrage opportunity, and as a byproduct, according to what we have done, this kind of price are just conditional expectations of the payoff with respect to equivalent martingale measure. Okay? So I want to do the proof of this lemma because I have explained everything. So are you okay with this? So I repeat that from the definition, okay? I am an arbitrage free price process if my final value is this one and if the new market is arbitrage free. Okay? I have proved in theorem 1 that to say that a market is arbitrage free means that there exists an equivalent martingale measure that make all these quantities martingales. If all these quantities are martingales, it implies that these one are martingales. And so that the Q I found from theorem 1 is also an equivalent martingale measure for my initial market that make just capital A, the martingale under Q, something that I write through this equality. Okay, it's the martingale condition. Okay. Clear or not? So I have this one without a proof because it's exactly what I have said. Okay. Okay? I continue. Lemma 13. I say the following. What is interesting with this notion of price is that a priori, if you have a look on this, I have a price that depends on Q. Okay? It means that I may have a lot of arbitrage-free price process. I don't have the unicity a priori. What we are going to see now is that if I work with a contingent claim that is replicable, in fact, this price here is independent of the choice of Q. Okay? So you can take any equivalent martingale measure. If my asset is replicable, all the arbitrage-free price process will be the same. That is, the arbitrage-free price process will be, in fact, unique. Okay? In the case where my asset is replicable. So, if NA is fulfilled, and if U is replicable, then I have the following. First, the arbitrage free price process is unique. Okay. Then, for all Q belonging to the set of the equivalent martingale measure, AT is equal to the expectation under Q of U given FT. Be careful here. From lemma 12 to lemma 13, here there exists a Q, and then for all, it's not the same thing, okay? From lemma 12, I know that there exists at least one. And I just say that, in fact, it works for all in the case where I am replicable. Okay? And finally, I said also the following, that if I want to replicate in this situation, okay, so HT at T belonging to 0 capital T is the replication portfolio for my contingent claim U, if and only if and only if I have what? If and only if, so I can write it this way. For all T belonging to 1 capital T, AT is equal to M over line U plus HS. So I have an equivalent condition in order to ensure that my replication portfolio, that I have a replication portfolio, that is okay. Is it possible, so I know that I am replicable, to check if I replicate with this strategy, okay, but it's equivalent to check that this relation is fulfilled. Here, with the at is the portfolio with all the assets, that is self-financed, so I don't need, in fact, the quantity of non-risky assets to describe it. And here, you have the quantity of risky assets related to this portfolio. Okay. The proof is not that complicated, it's just to play with the definitions here. Okay? So let's do the proof. So NA is fulfilled, but it means that there exists at least one equivalent martingale measure. Okay? And U is replicable. So U is replicable means that there exists H belonging to HD such that U is equal to what? And also there exists an A belonging to R such that U is equal to A plus H S capital T. That's the definition of being replicable at price A. There exists a financial strategy starting from small a in such a way that the final value of this strategy, that is this one, gives me exactly my contingent rate. Okay? Everything being written in the actualized way. Okay. So I want to prove that, okay, the arbitrage-free price process is unique. What is an arbitrage-free price process? It's something so that there exists Q with this. Okay? So let Q belongs to the set of the equivalent Martin measure. If I start from this one, and if I take the conditional expectation, okay? Hmm? Not by definition, but by an argument we have already seen together. So I have my equality and I take the conditional expectation. I obtain what? A plus what? I know that this one, what I have inside is a martingale under any equivalent martingale measure. So I have H S small t. Okay, so my arbitrage free price process, okay, this one is equal to A plus HST. And I have to deduce the unicity, but in fact it's a job I have already done. Okay? So if you come back to something that is called in the course remark 5, in the remark 5, we have seen together that if I have two self-finance financial strategies that replicate the same contingent claim, necessarily the values at any time of these strategies are equal. Okay? It's a proof we have done. Remark 5 implies the unicity of small a and the unicity of HST, so the unicity of 80. Because if I replicate, in the case of absence of arbitrage opportunity, small a is unique and HS small t is also unique. It's a proof we have already done together. It was the remark 5. Ask c'est pénible, mais vous verrez quand vous serez en stage, ça sera vachement moins rigolo qu'ici. Hein. Une boîte, il faut beaucoup plus attention à ce que vous faites attention à l'université. Il faut s'entraîner, en espérant pour vous que vous n'aurez plus de masque au moment de votre stage. En espérant que vous aurez un stage, en espérant que vous puissiez sortir de chez nous, pour essayer de trouver un stage. Okay, so the arbitrage-free price process is unique in the case where U is replicable. And in fact, this is just an extension of what I have proved for the arbitrage-free price at the beginning of this session, saying that in the case where my contingent claim is replicable, the set of the arbitrage free price is unique. Okay? And is given by the expectation under Q of U for any Q. So I have this one. Now I have the definition of an arbitrage free price process with the fact that there exists Q such that A of t is equal to this one. Let's prove that in fact it works for any Q. It's exactly the same kind of argument here. So I erase this one. So if I am replicable, but in fact I have to say nothing. Because, okay, it's tautology. Huh? If you have Q that is equal to A plus HS capital T, okay, but for all Q belonging to the set of the equivalent martingale measure, for all of them, okay, but I have the expectation under Q of U given Ft. That is, it's exactly what I have written previously, A plus HS small t. Okay, and so what? I have something here that is totally independent of Q. Okay, so this is true. So this one is equal to this one. And from what I have written previously here, it's exactly AT. Okay, so if you want here, my Q is fixed. I have this, Q0. Okay, having this relation. If I take an arbitrary Q, taking the conditional expectation in this one, I just use the fact that here it's the final value of a martingale. Okay, and so here you have exactly the AT defined this way here. Okay, so if I have it for one, I will have it for all, but just as a consequence of this one and the fact that here you have the finite value of the discrete stochastic integral that is known to be a martingale under any equivalent martingale measure. Okay. And for the last, what is the argument for the last one? Well, so, to check if you replicate the contingent claim, I said that it is equivalent to check that I have this one. Okay? So, if you have understood what I have said before, what is the meaning of this? It means that the replication condition is this one. So, replication condition, there exists H belonging to HD such that U is equal to A plus HS capital T. This is the replication condition, but since I know that the arbitrage free price process is a martingale under Q, okay, under any Q, but this small 3 here means that in order to know the martingale, it is sufficient to know its final value. So if I know that I replicate, that is something that is related to the final value of my strategy. Okay, to say that I know it at the end is equivalent to say that I will know it at any time because I am a martingale. Okay, and because that the martingale at time t may always be written as the conditional expectation of its final value given f at the time that I consider. Okay, so to replicate, that is a condition on the final value, is equivalent here to say that AT is equal to A plus HST for any t. Why? Because, okay, but this one is of course obvious because I have to take just small t equal to capital T to have this side, and to have this one, okay, I just take the conditional expectation. Okay, so this last condition just means that, I repeat, know a martingale at capital T is equivalent to know it at every time before taking the conditional expectation. Martin wrote, M of small t is always equal to the conditional expectation of M capital T given F of small t. Okay? Okay. So, keep in mind what I want to do in this course. Okay? I just, yeah. Que A est égal à. Ouais. Alors pourquoi j'ai ça? Oui, je vois ce que tu veux dire, tu as raison. Mais je dis que c'est évident. J'ai oublié de le dire. C'est une bonne remarque. It's the same thing here also. Small a I have written here. U is replicable. From what I have done at the beginning of the session, I have a single, in fact, arbitrage free price because the expectation under Q of U, okay, is independent of Q. So here, in fact, you have necessarily this one because all the expectation under Q of U are equal and equal to M over line U, okay, the unique point inside. So, right, okay. Small a here is necessarily equal to M over line U because M over line U is the expectation under Q of U, the quantity that I know to be independent of Q, okay, and equal to M over line U. Okay? But you're right. So the price of replication is necessarily M over line U because I have a single element in the set of arbitrage free prices. Okay? So, to continue your remark. So, keep in mind what I want to do in this course. In this course, a priori, so I have an initial market with assets that I am able to buy, to sell. Okay? And the idea is to propose a price and also hedging strategies related to what I call contingent claim. Okay? So what happens if I want to sell, okay, to someone a contingent claim, at which price I will do, and what I will do in order to hedge the risk related to the sale of a contingent claim. But in my situation here, I have a perfect answer. If I have no arbitrage opportunity and if my asset is replicable, okay, you have the unicity in the definition of the arbitrage free price process. That is, in this situation, also, okay, the value of any replication strategy. Okay, so it means that if you compute these conditional expectations here, you will have the arbitrage free price that will allow you to build, okay, a replication portfolio. So in the case where my asset is replicable, okay, I have a perfect answer to what I want to do at the beginning. That is how to price through the definition of arbitrage free price, and also to hedge because the definition coincides. The notion of arbitrage free price in this situation is related to the value of any replication portfolio. Okay, so replicate or to price give rise to the same associated values. Okay, and in the case where I am replicable, I have a perfect answer to everything. Okay, I have a perfect answer. In particular, suppose that all the assets are replicable. Okay, meaning that the market is complete. If the market is complete, you are going to do the job. You are going to be able to do the job for everybody because all of them are replicable. So in fact, if you have understood, it remains to answer one question, in fact, in order to finish what was my initial objective. That is, what can I do if my asset is not replicable? Okay? What can I do if my asset is not replicable? In the case where is it, okay, I have a good notion of price that is unique, okay, according to what we have done, and that is associated to replication strategy. When I am not replicable, of course, it's not possible to define the replication strategy because I am not replicable, and the notion of arbitrage free price won't be unique. So I don't know which one to choose, okay, among them. And what we are going to do now to finish, let's say, the most theoretical part of the course, is to answer to what happens when U is not replicable. When U is not replicable, we are going to see that using what we have done previously, it should be possible, if I suppose that A hypothesis is fulfilled, it will be possible to over-replicate this asset every time. But when I over-replicate, okay, my objective is to over-replicate at a minimal price. We are going to prove that the minimal over-replication price is also given by M over line U. That will be the smallest price at which you will be able to over-replicate the asset. Okay? So if you want to sell this asset, you won't be able to perfectly hedge, but you will be able to over-hedge, let's say, at a minimal cost. Okay? So it's the best you will be able to do in this situation. Okay? Questions before to continue? Okay? C'est pas OK du tout. Vous comprenez rien. Votre rire ne me rassure pas. So I repeat. What I have done now, tell me that if I have studied theoretically my market, proving that the innate hypothesis is fulfilled, okay? I don't have arbitrage opportunity that is equivalent to prove that there exists an equivalent marketable measure. Okay? So if I give you a model, you are able to check if this condition is fulfilled or not. So if NA is fulfilled, I said that in my situation, if I know that an asset is replicable, okay, I am able to define without ambiguity a notion of price, that is the notion of arbitrage-free prices, okay? So that can seems to be a little bit theoretical when we see it for the first time, but according to this little lemma, we see that the arbitrage-free price is related to the fact that I want to replicate my asset, okay? So it's exactly what you do in the case of the Black-Scholes model. In the case of the Black-Scholes model, what you consider as the price, okay, is just the replication price. That is also, in this situation, considered as a price that makes the new market extended with the new asset arbitrage-free. Okay? So it is okay when my market is when my contingent claim is replicable. In particular, in my market is when my market is complete, that is all contingent claims are replicable, but I will be able to do the job for everybody. Okay? If the market is not complete, there exist assets that are not replicable, and what we are going to try to do now is what can we do in this situation? Okay? When there exist assets that are not replicable, what can we do? We won't be able to replicate, but we'll be able to replicate, to over-replicate at a minimal cost. Okay? So it's what we are going to do. I want to answer what happened, what can I do in the case where I want to deal with a market that is not replicable, and with a contingent claim that is not replicable. So in the next session, I will give you some particular examples, okay, of some special cases, and you will see that what we are going to do is to study the theoretical properties of the market. It fulfills NA or not. It is complete or not. In the case where it is complete, I will be able to give you explicitly what is the value that is unique of the arbitrage-free price process and to deduce the composition of an hedging portfolio in most of cases, okay? And in the case where we are going to have markets that are not complete, okay, we'll try to over-replicate at the minimal price we are going to find now. Okay. I write this, okay. What can we do when U is not replicable? So keep in mind that from what I have done at the beginning, I know things in this situation. In this case, I am M overline U that is strictly greater than M underline U. Because I have proved that to be equal or to be strictly greater in this situation allow to give me if I am replicable or not. Okay? So in this case I have this one and the set is the open interval. So you have, in this situation, I repeat, an infinite number of prices that are compatible with the notion of arbitrage free prices. And of course, it's something that is not possible to support. If I ask you, okay, I want to sell you something, just choose a price in this interval here, okay? I have a problem if I do this. So we are going to prove that we are not able to replicate, but we are going to be able to over-replicate. So I just remind you the definition of over-replication. It was just to be clear with the notations here. It's the definition 13. So it's not the definition of being over-replicable that I will introduce in this definition because it's something we have already seen together, but I will introduce two new things here. So I know that U is replicable at price small a, or excuse me, over replicable at price small a if there exists an H belonging to HD such that A plus H S capital T is greater than E. I am not necessarily equal, but I am for sure greater than. Okay. So I introduce this notation in the definition. I will denote by A of U the set of the over replication price. So the set of the A belonging to R such that there exists H belonging to HD with A plus H ST greater than U. Okay? So it's the set of the initial price that allow me to over replicate using self-finance strategy. Okay? And the one we are going to be interested in is the minimum of all of them, if it's possible to obtain it. Okay, and I will denote by alpha by the infimum of A of U. And the last big theorem of this course will be this one. I will write it here in order to do the proof. It's the theorem 4. The fact that I have a perfect characterization of the set of the arbitrage free and the over replication prices. Okay. I said that A of U is in fact something of this form where alpha is given by M overline U. So it means that in this situation, the best thing you can expect is to be able to over-replicate at the minimal price, that is M overline U. Keep in mind that this one is the supremum over Q of the expectation under Q of U. Okay? It is the minimal price at which you can do the job. And now the job is to do the proof of the theorem. So
when you over replicate, you create an arbitrage opportunity?
no. replicate using self-finance strategy. Okay, so no. Why do you want me to create arbitrage opportunities?
Because in the end, you have two assets that you know which asset will have the pricier than the other.
A priori, when you have a contingent claim, you have no notion of price of it. You want to sell, for example, a call option that is not possible to buy or sell on the market. Okay? My idea is to say, oh, okay, I want to sell this one, at which price I can sell it. If you find a replication strategy, okay, it is fair to sell it at the replication price. Okay? If you are not able to do this, what you are going to do for yourself is to see if you can over-replicate. Okay? So it's not the price that you define, but it is the over-replication price. So I won't say that the small a involved in the definition will be the price of my contingent claim. It will be the price, the minimal price at which I will be able to over-replicate. So if I want to over-replicate, it's the base thing I can do. Okay? So be careful, huh? I don't define, okay, I can, it's the over-replication price if you want of an asset, but that is not the price. Okay? Not the price, because I'm not able to define, because for the arbitrage-free prices, okay, the only notion that is admissible as a price, I have an infinity of price, and you won't be able to choose among them. Okay, you don't have, a priori, doing what we do here, you don't have rational criteria in order to select one price more than another here. So since I am not able to do this, I just say that, okay, forget this, I want to over-replicate, because to be sure that when I will sell my product, I won't have problem at the end. Okay, I will be able to deliver my product in any cases. But of course, to do this as a cost. If I want to be competitive for a customer, I want to do it at a minimal, and the possible minimal cost. I will prove what it is, this minimal cost. Okay? But it's not a notion of price as in the case where my asset is replicable. In the case where the asset is replicable, I don't have the choice, because if I don't do this, it will be possible to create an arbitrage opportunity. Okay? So the only thing that you can say here is that if this one is 10 euro, okay, and if you see someone that wants to sell the asset for 15, you just say, oh, I am able to do better. So it's not an arbitrage really, okay? But just the fact that you are more competitive and that you will have the client that you want, okay? It's the best I can. So I don't have the time to do anything here, but just show you what will be my objective, okay? So I want to prove that first, that the interval has this form here. So I have to do two things. I will show you the sketch of the proof, and I will record my video during the end of the proof. Okay? So, first of all, keep in mind that A of U is the set of the A belonging to R, such that there exists H belonging to HD with A plus HST that is greater than U. In particular, I say the following: if small a belongs to AU and B greater than A, what happens for B? What happens for B? If you are able to over-replicate at one price, yeah, okay. If you are able to replicate or over-replicate at price A, for sure, taking the same H will be able to over-replicate at price B that is greater than A. So if A belongs to AU, then and B greater than A, then B belongs to AU. And so it means that I have two possibilities. So I have an interval that is unbounded from the right, okay? The right part of the interval. So it means that I have two possibilities. AU is equal to, I have my infimum that is inside, or my infimum is not inside. I don't have the choice, okay? Because I am an interval that is unbounded from the right. Oui. C'est le... Non, le théorème il est là. D'accord. Le théorème il vous dit que tous les prix de surréplication sont donnés par cet intervalle. J'ai le prix minimal de surréplication qui est donné par cette quantité. C'est ce que je veux démontrer, mais il me reste 1 minute, donc je n'arriverai pas à le faire. Ça va me prendre au moins 3 quarts d'heure pour faire ça. Et je vous montre l'idée, la preuve, que je finirai la semaine prochaine en vidéo. First, I prove that I have an interval of this form, or of this form, because I am unbounded from the right. So I am an interval that is unbounded at the right part of the interval. Okay? So, for the beginning, I have this. So, if I want to prove my things, I have to prove 2 things. I have to prove that the lower bound is inside. So, first step, I have to prove that the lower bound is inside. I will prove that A of u is closed. Why it is closed? We'll see, but it's not that complicated to see that it's because I have a large inequality. Okay? I have a large inequality, so in fact, defining A of u this way, we will obtain a closed set. If my set is closed, I am in this situation. I have to work to do this, so if I prove this, I will do next week, I am in this situation. The second thing to prove, okay, second step, that alpha is equal to m over 9u. Okay? That is, the minimum of the over-replication price is given by the supremum of the expectation under Q of u, or Q being an equivalent martingale measure. Okay? So in fact, there is one part that is not that complicated to do, because if I have this, okay, if I take the expectation of this quantity with respect to an equivalent martingale measure, this term disappears and I have A greater than the expectation under Q of u. So to prove this one, it's not difficult. I just have to take the expectation under Q in this inequality. I obtain A greater than the expectation under Q of u. Okay? It is true for any Q. Okay? And in fact, I can deduce this one. For the other inequality, it's a little bit more complicated, and I will do it next week. Okay?